Okay, hello everyone. Hello everyone, welcome back to Calculus 1000. So, being able to finish the basics of differentiation, the definition, some necessary conditions specifically that every differentiable function is continuous. Now we have to work on our basically competency of differentiating. So this is what you guys are good at from high school, which is differentiate. Use the rules. Turn on this machine of differentiation and differentiate more functions. Yes? As you know, there are collection of rules that we have to learn here. And today we are going to start basics and cover the first one. And as we go on in the next few sessions, each session will start with some new rules, differentiating some new functions, and then we will build on this recipe for differentiation. So I'm trying basically turn you guys into machines of differentiating machines that craves for functions to differentiate. Well, you are already like that. Well, we're just trying to clean it up a little bit and connect it to some of the other stuff that we will learn. Before I start, is there any questions, any comments? Okay, so differentiation rules. We will start with these simple, basic ones. Again, I'm expecting that you already know all these ones. In all these rules that we are working, the assumption is that let f and g be differentiable functions. And then we want to see if the new functions that we create out of these ones, are they going to be differentiable as well? For example, is fx plus gx or minus, are these differentiable? Are these sum or difference of two differentiable functions? The answer is yes, and actually we know how the derivatives are going to play or form the derivative of this summation or difference. This is called summation rule or addition rule, difference rule. And there is another piece that I will write in the same place when you have a constant multiplied to that. This is not necessarily a new one because, well, it will be covered by the product rule. But I want you to know this, that in general, derivative and scalar and constant multiple, they work nicely together. So just constant comes out. You don't need to differentiate that. The second thing, and well, the other operation that we are interested in knowing the differentiation rule for is the product one. Is the product of two functions differentiable? If yes, the answer is yes. If yes, then what is the rule of differentiation? In this case, well, needs a little bit of work, but turns out that, okay. This is nothing but the derivative of first one times second one itself, plus the first one itself times the derivative of the second one. This is called product rule, and we will try to use it in different scenarios. How about the quotient? Well, in the case of quotient, we have to be careful, as always we did, that the denominator should not be 0. So that way, that's the only way we can say that this is even defined. Forget the differentiability. So in that case, the rule is a little bit more complicated than the other two that we had, but it has some similarities to this case, which is coming from a right place. You will see that. This will be derivative of numerator times the denominator itself, as we had for the product rule, the first one, second one kind of thing. And then numerator times the derivative of the denominator. The first thing that you see is this one is not plus. You have to subtract. And again, if you approach that quotient in the right way, then you will figure that out yourself, why this is happening. But then in the numerator, in the denominator, you will get this part squared. Okay, that's called quotient rule. We also have something called chain rule. The chain rule, we'll try to work with it in different situations, but this is about differentiating composition of two functions. What if I have f evaluated at gx? Well, you can read this in different ways, but I like to keep this in inner function, outer function. And we call it chain rule because you start from the most inner function and you move out and differentiate one by one. So inner one, then the outer one. Okay, here is what you should be careful about. Inner one, the inner function is evaluated at x. So when you differentiate, you evaluate it at x as well. The outer function, you differentiate. But outer function, note that it is evaluated at gx. So now, when you differentiate it, it needs to be evaluated at gx, not at x. And the reason this is called chain rule is more clear if you try to do this. This is just as a result. As a result, you do it for the composition of three functions. Now, exactly why we call it chain comes here. You do the first inner one, then the second inner one, then the outer one. So you start getting them from the inner to outer, but each one is evaluated on different things. So their derivative must be evaluated on different things. So the inner one, the derivative evaluated at x, the second inner one evaluated at f at x, sorry, h at x. Why f at x? The very outer one is evaluated at g at x, g at hx. I think my mic is dying, so let me change this. Can you hear me now? Is it good? Okay. You can hear me with mic or without mic. I can, I can be loud. Okay. And the last thing that I want to add here is the power rule. This is not difficult actually to show with the works that we have been doing. This is about what is the derivative of different powers of x. And what comes out is nx to the power 1 less than n. Well, there are few of important ones for this one. For example, if n is 0, well, no one gets this one from the power rule, but you can see that it works. Derivative of 1, I should have said, but this will be 0. Derivative of x itself, this is x to the power 1. 1 comes, and then x to the power 1 minus 1, which gives you 1. There is this derivative of root x. Derivative of root x, you can see it as derivative of x to the power half, yes? And then apply the same rule. It will be half x to the power half minus 1. Yeah? But if you simplify that, I mean, I want to erase actually the parts that I wrote. I just wanted to make sure that you see what I'm doing there. If you calculate this thing, what you will get is 1 over 2 root x. You can always get those ones from the power rule, but this one and the one that says what is derivative of 1 over x, what is derivative of 1 over x? Yes? Negative 1 over x squared. And the way you see it is x to the power negative 1. Apply the power rule, and then play with it a little bit, and that's what you will get. There is also something I would call a chain plus power rule. This is when you have something to the power n. That thing could be x itself, or that could be in general a function of x. We write it as u. U to the power n, the derivative is n u to the power 1 less. So far, it's like the power rule. But if you look at the chain rule says that your derivative of your function is still there. F was u to the power n, or x to the power n. So this part is exactly what I've written down. But chain rule says that you have to multiply it by the derivative of the function that was inside your power function in particular. So that would be, you have to multiply the derivative of u to that piece that we had from before. Okay? So I trust that you have worked with these ones. You already know it. We need to just quickly go through some examples and make sure that everything is in place. And am I all right to consider that you all know these rules well? Can I see the hands? Can I? Okay, that's okay, good. Yes. Okay, then just do the examples on the handout that I gave out yesterday, and just do more things. Just differentiate. Oh, I'm doing on board. Don't worry. I won't let you guys down there. Let's start with example 1 there. Yes, there are some, you can pick it up from here. The type of work that I want you to show, for example, what is the function? Ooh, okay, yes. Oh, I thought yesterday you guys got some. Okay, good. You're on camera, just remember. Go like that.
No, I didn't.
Okay, the table of values and the table of values of f prime, the derivatives, are given. Actually, could you please take some back there in case someone, just leave it somewhere there so that they can. Thank you. So for this specific example, we are trying to just see that you can do the rules. Let me do the easy one. I usually do the easy one. The difficult ones are yours. That's how this works, okay? So I'll do the first one. For example, here, the first one, h of x is x f of x minus 2g of x, yes? Now, I want to find the derivative of this. First thing I see, this is difference of two functions, so I have to differentiate each piece and then subtract. But the first function here is product of two functions. One is x, the other one is f of x, so I have to apply the chain rule here. Derivative of x times f of x plus x itself times the derivative of f at x minus the constant multiple rule. I factor out this too, so constant multiple works nicely with the derivative. So this comes out, and we have g prime at x. Okay. That's the derivative. What more I want to find h prime at this specific number, 2. Oh, wait a minute, I'm not done yet here. Derivative of x is 1, so I can jump that step and just erase that. Yeah. So now h prime at 2 is f at 2 plus 2 times f prime at 2 minus 2 times g prime at 2. And then we use the values from the table. F at 2 is 3 plus 2 times g, or f prime at 2. F prime at 2 is negative 1 minus 2 times g prime at 2 is negative 1. You have everything there. You just need to do the arithmetic here, yes? 2, 5 minus 2. Oh, these two cancel each other. You get, yeah? Works like that. Are we all good on that? Yeah? Can I give you 1 minute to do part 2? 1 minute is a lot. Go ahead. So you try to do it on the notes with your friend. Please do it. So we are trying to check that. Yes, please.
1 minute still.
That is also good. You're doing extra work here. Yes, the derivative of 2 is 0. So there's a bracket around this one. See, the derivative of this thing multiplied by negative, yes? You didn't multiply this by negative. It didn't change the result, but I'm just saying that, yeah, it will work that way as well. I should hear the noise of differentiating machines. Like that. Do I have some numbers there? Did anyone get the value for this one? Can I see? Maybe another 10 seconds. Yeah. So this is product of two functions. So it goes like the derivative of first one times second one plus the first one itself times the derivative of second one. And here, now, I have difference of two functions, but the second function is constant. Derivative of constant is 0. So I don't need to be worried about that part, but this part here is product rule, f prime x gx plus fx g prime x minus 0. Well, I can write or not write. That's cube plus f at x, g at x minus 3 times 3x squared. That is the derivative, but we need to evaluate it at 1. Was it 1? Yes, it is 1. So in this case, then we have f prime at 1. F prime at 1 is 3 times g at 1 is 1 plus g prime, or f at 1, negative 2 times g prime at 1, which is 2, times, what is it? 1 to the power 3, okay? Plus, f at 1 is negative 2 times 1, minus 3 times 3, 1 squared. Yeah? I'm just putting in from the table, yes? I may make mistakes, but did anyone evaluate that value? What was that number? Did anyone get that number?
Negative 6.
Negative 6? I'm okay with negative 6. If it is wrong, it's wrong. It's just a number. Yeah. It's negative 6. How many of you got negative 6 there? What? Did we get other numbers? Did we get any other numbers? 16. Wait a minute. Okay. Let me see. Oh my God. I didn't want to do all this work. Negative 5 times 3 negative Oh, we were close. Oh man, come on. Negative 16. Yes, thank you. Numbers, yes. Okay. 3 and 4. I will leave those ones to you. Maybe I'll do one of them. Which one do you want me to do on the board? 3 or 4? 4? 4? Okay, I'll do 4. The other one, you have it on the paper, so you can do it at home. So h at x is root of 4 f of x minus gx. And we are trying to find it at 4. Remember what I did with this square root of x, the derivative of square root of x? I can do the same story with the derivative of square root of u. And as the same result will give me d dx of u square root of u is 2 over root u is down there, like as we had 1 over 2 root x there. But then chain rule says that you have to multiply it by the derivative of u. So the same story holds here. H prime x then is u prime for f of x minus gx prime over 2 root 4 f of x minus gx. Then this is some difference of two things. Constant multiple will give you that. And that's the derivative. Then we are trying to find h prime at 4. So that means 4 times f prime at 4. F prime at 4 is 1 minus g prime at 4 is 4 divided by 4 times f at 4 is 1 minus g at 4 is 0. So that is 0 over root 4, which is half of 0 or just zeros. Any questions, any comments here? So the questions like this basically tells you, okay, oh, I made a mistake, it seems. Okay, let me start. Yes? Oh, this 2. You mean this 2? Where is this coming from?
The one in the actual problem that we did.
Oh, where did it go? It is here. Don't you see? It's there. Yes. Yes, sorry, thank you. The number is good still, it's 0. Yes, yes, you're right, thank you. How about let's do example 2. Example 2, bunch of functions we want to differentiate. So we remember what we did. I will do a few of them, but I'll give you maybe 3 minutes. 3 minutes. Don't sit there looking at me. Don't sit there talking to your friend about other things, but those 5 functions. Try to differentiate as much as you can. Go ahead. 3 minutes starts now. You have 1 minute left.
I'm fully frank.
Ten seconds. Okay. Well, these are easy. Let's do quickly some of these. F of x is x cubed minus 4x squared minus 4x plus 2. Then the derivative, this is sums of some multiples of x to the power n. You use the rules that we have. You go 3x squared minus 8x minus 4. The third function, that's easy as well. I'm doing only the easy ones. 4x cubed minus 1 over x. Then the derivative is, derivative of root x is 1 over 2 root x. Thank you. This guy, 4x cubed, gives me 12x squared. Thank you. And negative 1 over x, the derivative. There is a negative 1 over x squared. That negative goes away, and then we get this. I just need to do 2 more. These are easy ones. Square root of a function, the derivative is going to be derivative of that function under the square root over 2 root of that function. And the derivative of this guy is 6x minus 4. The fifth one, this is power rule plus chain rule. Oh, sorry, this is prime, yes? I'm finding the derivative here, yes, okay. So I have a function to the power n, derivative of that function times that function to the power 1 less. So I do this, the derivative of that and then divide that. But that means I have 3 times root x is 3 over 2 root x derivative, yes? Minus 2x. That's the derivative of that function times 3 root x minus x squared plus 3 to the power 2. And that's what we get there. Would you like to do an eye clicker question before you go? Let's do an eye clicker question. Why the quality of this thing is... Is it clear on your screen? What is the function there? No, you should see that. That's, oh my God. Okay. So we have two functions, f and g. hx is f at x, g at x, minus 2 or plus 2? Plus 2 over x squared. I don't know why. X squared plus x. The question is, what is h prime at 1? We know that f at 1 is given, f prime at 1 is given, g at 1 is given, and g prime at 1 is given. What are those values? 2, 0, negative 2, 0, 2, negative 3. Negative 2, 0, 2, negative 3. Go ahead, please. Pardon?
The line clicker says that the denominator is x squared plus x.
What did I? Oh, you're right. Sorry. Thank you. I have two good examples at the end of the handout, so let's finish this as soon as we can. 30 seconds, and then I'm closing the poll. Ten more seconds. Quotient rule, derivative of numerator, but derivative of numerator also has the product. This part is 0, so I go that times g prime x times the denominator divided by, okay, minus fx gx plus 2 times derivative of the denominator over the denominator squared. The question says set this one, find it for 1, yes? So f prime at 1 is 0, so this will go away. F at 1 is negative 2 times g prime at 1 is negative 3 times. This is evaluate at 1, yes? So that is 2 minus f at 1 is negative 2 times g at 1 is 2 plus 2. Plug in 1 here, that is 3, and that is 2 squared. What did we get from that? So this is negative 6 times 2, that's negative 12 minus. This guy is negative 4 plus 2, negative 2 times 3, negative 6 plus 6. Yeah? Did I do that part right? Negative, negative. Is there any answer like that in the minus 6 over 4? It's positive 12. Thank you. Saved me. And then that is 18 over 4, which is 9.
There you go.
Yes, after making few mistakes. D. Okay. Oh, I have only 5 minutes. The last example. Any questions, any comments before I start the last example? So the last example is a good example of, okay, we learned all these things about derivatives. Now we can find derivative of millions of functions, so many of functions. Remember that to start with, the definition of derivative comes from a limit. We want to reverse this process. Now that we have the machine of differentiation rules, if we can turn a limit into limit of derivative of a function at a given point, then we can use the rules of differentiation, derive it, and then evaluate the limit without any pain. Well, this easy example is the first one. Let me write this. So limit of x cubed minus 4x squared plus 3x minus 1. I want to see this limit as limit of the limit that defines derivative of a function at a point. Okay, there are two things. I want to see if I can turn this to the limit that defines derivative of one function to at a given point. The given point is here. You can see it because remember the derivative of a general function f of x at 1 is given by that. Do you see any similarities between those two things? Well, both of them, x approaches to 1. Both of them have x minus 1 in the denominator. The numerator, now we have to figure out to turn the numerator to the numerator of the right-hand side. But on the right-hand side, there is a function, and we have to make sure that we find a function such that when I write that function minus f of that function evaluated at 1, I get this thing here. So the question is now, what is the function such that f of x minus f at 1 gives us x cubed minus 4x squared plus 3? What is such a function? You said what?
Minus 4x squared.
X cubed minus 4x squared. Like that, yes? And then we go see, okay, f at 1 is then 1 minus 4, which is negative 3. So that means that f at x minus f at 1 is x cubed minus 4x squared minus negative 3, which is what we have there. X cubed minus 4x squared plus 3. So we found the function, which is this one. We found the point. So this limit is of this form. But we know that if function is differentiable, this is nothing but f prime at 1. Yeah? That's going to be f prime. I have f. I can differentiate it. What is derivative of x cubed? 3x squared. What is derivative of 4x squared? 8x. I differentiate it and set x equal to 1. And that gives me 3 minus 8, negative 5. See, I didn't do any limit tricks. You remember, if I wanted to do this one last week, I would say, oh, I want to do the quotient law. Didn't work. Denominator is 0, 0 over 0. We have to factor. We have to cancel. I didn't do any of those ones. What I did instead, I said that this limit is limit of a function, limit that defines derivative of function at 1. I found a candidate for that function. I used the differentiation rules, evaluated that one. Before, just give me 1 minute. Just give me 1 minute. You may say that I can do this without all those pain. If you believe this is not a strong enough tool, try to do example 2 yourself. Without doing this trick, example 2 is going to be a painful task. You don't believe me? Do it at home. Have a great day. Have a good weekend. See you all on Monday. I just sent it to the course coordinator. Have access to that. He has promised he will do it. Don't worry about it, okay? If the words comes to words, I'll say that I gave you.
I don't know if I can do 2, Brenda.
I didn't take anything you want.